Let's continue our exploration of analyzing data when we have a single quantitative response variable, but we have multiple groups, and that's due to a single explanatory categorical variable. And each of the different categories are the groups. And what we're trying to do is to model or predict that quantitative response based upon group membership. We are talking now about how to look at specific research questions rather than the omnibus research question. And in the last video, I told you that we can use multiple comparison procedures in order to analyze the data specifically, and when we make inferences, to control the type 1 error for a family of comparisons all at once rather than for a single comparison. Here are some of the common multiple comparison procedures that control error. Now, when I say some of them, there are probably in the neighborhood of 100 different multiple comparison procedures, and no, I'm not exaggerating. And so I have selected 3 of the most common ones. Tukey's HSD, or honestly significance difference, is for two-sided confidence intervals, and it's when we're interested in looking at all pairwise comparisons, which I would argue is the vast majority of the time. If you think about the example that we have been following through, in which we have 3 different worldviews and we're wanting to see if they differ in terms of their perception of risk on flying an airplane, we're probably going to be interested in whether the hierarchical list is different from the egalitarian, whether the hierarchical list is different from the individualist, and whether the egalitarian is different from the individualist. So we're probably interested in all pairs and looking at all pairwise comparisons. That is, looking at 2 at a time, but ending up to look at all possibilities of 2 at a time. Chaffee's method, we can have two-sided confidence intervals as well, but the difference with Chaffee's method is that you can create an unlimited number of intervals. You can look at differences between pairs. You could lump together 2 at once and compare it to a third. You might ask, well, why would we do this? Well, imagine if you had a control and 2 different treatments, and you want to ask the question, does having a treatment even work? Well, you might want to combine the 2 treatments and compare it to the control, and then perhaps compare the treatments to one another. So there's a variety of instances in which we might want to look at a whole bunch of different intervals, and one could do that using Chaffee. You can look at as many as you want without losing power as you add more intervals. That is, once you've decided to use Chaffee's method, then it doesn't matter how many intervals you construct. By contrast, Bonferroni's method, you specify the number of intervals in advance, and the more intervals you look at, the less power you have. That is, the wider those confidence intervals get. And as you know, wide confidence intervals have less information than narrower confidence intervals. But an advantage of the Bonferroni method is that you can do 1 or 2-sided intervals. That is, I could have a lower bounded interval. For instance, let's suppose I'm comparing treatment 1 to the control. I know that treatment 1 is going to be helpful. I just want to know how helpful. Well, I could set a lower bound for that interval to tell me that it's at least that helpful. And just like one-sided tests are more powerful than two-sided tests, one-sided intervals are more powerful than two-sided. Now, I'm giving you that overview here, but I'm also going to quickly add that we are in this course just going to focus on two-sided confidence intervals. That is the most common. That is what I teach in the first statistics course, and I'm going to carry on teaching that way here. But if you ever deal with a more advanced situation or a research situation, I want you to be aware that there are ways when you have theoretical expectations, like I hope you do in most of your research situations, there are ways in testing in a certain direction and creating a corresponding confidence interval. And if you happen to tune into video series that I do for more advanced courses, you'll see how to construct those. All right, now let's take a look at what we're actually comparing when we use these multiple comparison procedures. We are dealing with contrast. We are contrasting means. So a contrast in general is just a comparison of parameters. So you could actually create contrast for any parameters. You could create contrast for proportions. You could create contrast for variances. But we're going to focus on the most common kind of contrast, which is a contrast of means. Now, you see these mathematical formulas down here, and perhaps it puts your heart in your throat, but never fear, we're going to talk about this and work through this. So let's do so. Let's begin with looking at this, which is our parameter. Notice that it's a Greek letter and there's no hat. So this is a parameter for a contrast. Many of my students in the past have lovingly, and I put that in quotes, referred to this as pitchfork. They actually think that this whole idea is a little bit hellish and that pitchfork fits the bill quite nicely. But in fact, it is the Greek letter psi. PSI, the Greek letter psi. So this Greek letter psi is going to represent a contrast. And again, it could be a contrast of any parameters, but we're going to use means. Notice over here that I actually have a population mean. We're using the symbol for a parameter for means, that is the mean of a population, and that symbol is mu. The sub k indicates a group. That means that we are going to select means from particular groups that we specify. So for example, if I were to say mu sub 1, that's the first group. Or you could use some sort of other notation if you wish. For instance, in the example that we've been going through of worldviews, I could have mu sub I for individualist, mu sub E for egalitarian, and so forth. So this is the mean of the population of the group. Now you notice that when we look at this mean, that it has something in front of it. And so what is that in front of the mean? That is a weight. And so what we're going to do is we are going to weight the mean. So each group is going to have a weight associated with it. So if I'm dealing with mean 1, then the weight in front of this mean 1 will be weight 1. All right, so far so good. So we will have k equals 1 to capital K, where capital K is the number of groups. In the example we've been following through in this entire video series, we have 3 groups, so capital K would be 3. So this just means all of this here, let me go ahead and clear this and point to it. All of this here just means that we are going to add up all 3 of our means. K will be 1, K will be 2, and K will be 3. And we're going to add up all 3 of our weighted means. Now, over here, we have another formula. And what is that formula doing? That formula is defining what a legitimate contrast is. In other words, we will know that this over here is an actual contrast as long as, if and only if, the weights all add up to 0. Otherwise, it's not a contrast. So this first formula over here by itself defines a contrast, but it doesn't become a contrast unless we also can meet the properties of this second formula and all the weights add up to 0. As long as we have that, then we have a contrast. So let's look at an example. Let's suppose that I have, as we do in the data set we've been working with, I have 3 means. So K is equal to 3. So those means are going to be in the population, that is, the values that I cannot see, but that I'm interested in. Those means are going to be mean 1, mean 2, mean 3. And so let's create a contrast. I'll call it my first contrast. I'll put a little subscript of 1 to indicate it's my first contrast. Remember, we're doing multiple comparisons of means, so we're going to have multiple contrasts in a family. And that first contrast, let's suppose that I make the weight in front of mean 1 to be 1, the weight in front of mean 2 to be -1, and the weight in front of mean 3 to be 0. Now this can, of course, simplify so that we can just say that psi1 is equal to mu1 minus mu2. So all we have done here in this particular formula is we've purposefully set the weights for mu1 and mu2 so that we're contrasting the population mean of group 1 against the population mean of group 2. If you think about it for a moment, this format here, without actually seeing the psi, is what you did anytime you did a t-test in your first statistics course, anytime that you were estimating the difference in means. Whether you did the t-test for inference or not, you always were to estimate the difference in means by taking sample means. Now, in this case, we're dealing with population means, which we don't actually have. But if you think about it, this is something of interest to us. That is there a difference in the population mean of, say, individualist and the population mean of, say, hierarchicalist? This would be a way that we could look at that. If we knew the value of psi1, we would know the answer to that question. And as you might anticipate, we're going to be estimating these things. But before we do that, notice what my contrasts are. If I were to sum up my contrast, if I were to sum up all these different C's here, all these different W's, sometimes people indicate the weights as a C and sometimes they do it as a W, but we're doing it as W's. If I were to sum up all those W's, if I were to get the sum of all my W's, that would be equal to 1 plus -1 plus 0, which of course equals 0. That tells me that this is a legitimate contrast. So because I have a legitimate contrast here, I can actually include it in my family of comparisons of means. So what we just constructed is a pairwise contrast. Remember that in general, a contrast is just a comparison of parameters, but when we compare just one parameter to one other parameter, which is what we just did when we compared mean 1 to mean 2, that is considered a pairwise contrast. Now, when we have 3 means, such as when we have 3 worldviews in the present data that we've been working with, we can have 3 pairwise contrast. So we could have our psi2 equal mu1 minus mu3. And of course, the weights in this particular case would be 1 for group 1, 0 for group 2, -1 for group 3. And if we add up all those weights, that's going to equal 0. And then our third contrast could be mean 2 minus mean 3. And those weights would be 0, 1, and -1. So 3 groups will lead to 3 different contrasts if we're doing pairwise contrast. And so we have, by these contrast having 1, 2, and 3, this forms a family of all pairwise contrast. You could have a family in which you're just doing some of the pairwise contrast, but this is a family of all pairwise contrast. And I mention that because I already had indicated that when we're conducting a contrast that includes all pairwise contrast, that is, we're creating confidence intervals for all pairwise contrast, that the best method for doing that is the one attributed to Tukey's HSD test. So this would be what we use if we want to do all pairwise intervals for our specific comparisons. Now, what about complex contrast? That's also a comparison, but instead of comparing one parameter to another, we're comparing groups of parameters. Let's look at an example. So one of the things that we talked about when looking at the different worldviews, if you go back and look at the code book, you'll see that individualist and egalitarian are both considered low grid. Remember that it's a grid-group combination that determines whether someone's an individualist, an egalitarian, or a hierarchicalist. So suppose we were interested in comparing low-grid typologies to high-grid. Well, individualist and egalitarian are groups 1 and 3, so we're interested in contrasting groups 1 and 3 against group 2. So how could we do this? Well, one way to do this would be to average groups 1 and 3, the means from groups 1 and 3, and contrast it against group 2. And this would create potentially a fourth psi, a fourth contrast. So if you think about the weights here, the coefficients, we have for our coefficients half for group 1, -1 for group 2, and half for group 3. And that's a legitimate contrast because when we add all those things together, we end up with 0. So this would be considered a complex contrast. It's not really that complex, but anything that involves more than 2 parameters at a time, we call complex. When it only involves 2 parameters, we call it pairwise. Now, in this video series, I'm going to focus primarily on pairwise contrast, but in later videos, we're going to do some complex contrast, so you want to keep this little tidbit up your sleeve that we could have complex contrast. One other thing I should note about complex contrast is in the formulation that I've done right here, where I just averaged the mean of 1 and mean of 3, we're giving the mean of 1 and mean of 3 equal weights. So this is called unweighted means because we're giving them equal weights. Now you might say, well, why would we ever do weighted means? Why would we give them different weights? Well, imagine if there were twice as many people in the first group as there was the third group. Then if you really wanted the mean across both groups, that is the literal mean, you're going to have to give the weight for the first mean twice as much as you'll have to give the weight for the third mean. I'm not going to do that right now. I'm not going to focus on that. We're focusing primarily here on weighted means as we learn this. But as you think about down the road, dealing with more complexities, there's the possibility that we have unequal numbers in each of our groups, and subsequently we want to have a mean that is formed up of the individual means in proportion to how many people are in each group. Now, even if you have unequal numbers in each group, you can still do unweighted means. That might be what you're mostly interested in, is when I just average the two means together, regardless of how many people went into composing that mean, that might be, in fact, more aligned with your research question. When we have equal numbers in each condition, we call that a balanced design. So in this particular case, if the number in group 1 is equal to the number in group 2 is equal to the number in group 3, then this would be balanced. Now, my hunch is, I haven't looked at the data, but my hunch is that we have unequal numbers in each group here. But since we're only going to be focusing on pairwise comparisons, like the one right here, this pairwise comparison here, it doesn't matter that there's unequal numbers in each group. So in a balanced design, unweighted means and weighted means are actually going to be the same thing. But whether or not we have a balanced or an unbalanced design, whether we have the same number in our individualist group as our hierarchicalist group, as our egalitarian group, doesn't really matter here because, as I said, we're going to focus on pairwise comparisons of means. So to review, a contrast is a comparison of parameters. A pairwise contrast compares one parameter to another, and a complex contrast involves more than two parameters at the same time, and all contrasts are constructed such that the sum of the weights is equal to 0. Now, I have done my definitions in terms of populations. Obviously, we don't have access to the population, so we're going to have a sample of observations and do estimation, and we'll look at that in the next video.